Preparing for a Kubernetes and Platform Engineering at JPMorgan Chase interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you explain Kubernetes architecture and the responsibilities of its main components? Kubernetes is a control system that continuously reconciles desired state with actual state. The API server is the entry point, while etcd stores cluster data. The scheduler assigns unscheduled pods to nodes, and controllers create or repair resources. Each node runs kubelet and a container runtime. Networking is handled through CNI and kube proxy or an equivalent data plane. In production, I protect the control plane, restrict API access, monitor etcd, and design for failure rather than assuming nodes remain healthy. While answering, cover the control plane, API server, scheduler, controller manager, etcd, kubelet, container runtime, and kube proxy. Explain reconciliation, desired state, high availability, and why separating control and data planes improves operational resilience. Question 2. What happens inside Kubernetes after you apply a deployment manifest? When I apply a deployment, kubectl sends the manifest to the API server, which authenticates, authorizes, validates, and stores it in etcd. The deployment controller creates a replica set, and that replica set creates pods. The scheduler selects nodes, kubelet pulls images and starts containers, then readiness probes determine availability. I verify progress with kubectl rollout status and inspect events, pods, and replica sets. The key idea is asynchronous reconciliation, so submission does not mean the application is already serving traffic. Make sure to cover API validation, persistence in etcd, deployment and replica set reconciliation, scheduling, image pulling, container startup, readiness, service discovery, and rollout status. Mention asynchronous reconciliation and useful debugging commands. Question 3. How would you secure a Kubernetes platform for a highly regulated financial environment? I would start with strong identity federation, least privilege RBAC, and separate access for humans, workloads, and automation. Secrets belong in an external secrets manager with encryption and rotation, not Git or plain manifests. I would enforce signed, scanned images through admission policies, restrict traffic with network policies, encrypt data and audit logs, and isolate sensitive workloads using namespaces, node groups, and accounts. Regular access reviews, immutable audit trails, and tested incident procedures make the controls defensible during audits. In your answer, talk about identity, RBAC, least privilege, network policies, encryption, secrets management, image security, admission controls, audit logs, isolation, vulnerability scanning, and compliance evidence. Include operational controls without treating security as a single tool. Question 4. What are the key differences between Docker containers and Kubernetes pods? A container packages and runs an application process, usually through Docker or another OCI-compatible runtime. A pod is Kubernetes' smallest deployable unit and can contain one or more tightly coupled containers. Containers in a pod share an IP address, network namespace, localhost, and optionally volumes. I usually place one main container per pod, adding sidecars only when lifecycle and communication are genuinely coupled. Kubernetes schedules and replaces pods. It does not manage individual containers as independent deployment units. Be sure to mention that a container is a process isolation unit, while a pod is Kubernetes scheduling and networking unit. Explain shared namespaces, volumes, sidecars, lifecycle coupling, and why one container per pod is common but not mandatory. Question 5. How would you design a reliable EKS cluster for critical production workloads? For production EKS, I would use private subnets across multiple availability zones, a managed highly available control plane, and separate managed node groups for workload classes. IAM roles for service accounts provide workload-level AWS permissions without node-wide access. I would configure cluster and workload autoscaling, encrypted storage, controlled ingress, centralized logs, metrics, and traces. Terraform or an equivalent tool would make changes repeatable. Finally, I would test node, availability zone, deployment, and dependency failures before calling the platform resilient. Focus on multi-as topology, managed control plane, node groups, autoscaling, private networking, IAM, ingress, observability, backups, upgrades, quotas, and failure testing. Mention separating workloads and using infrastructure as code for repeatability. Question 6. When would you choose Helm, and how would you structure a production Helm chart? I use Helm when an application has repeatable Kubernetes resources with environment-specific configuration. A production chart should have clear templates, reusable helpers, sensible defaults, a values schema, consistent labels, dependency declarations, and documented upgrade behavior. I keep business logic out of templates, validate rendered output with Helm lint and template, and test charts in C. Secrets should come from an external manager rather than values files. Chart and application versions should be managed independently so rollback remains predictable. Cover packaging, templating, values, reusable helpers, chart dependencies, schema validation, naming, labels, defaults, environment overlays, secrets handling, testing, and versioning. Explain how to avoid turning Helm into an unmaintainable programming language. Question 7. How would you troubleshoot a Helm deployment that installed successfully but is not serving traffic? I first run Helm status and Helm get manifest to confirm what was actually rendered, not what I expected from values. Then I inspect pods, events, container logs, and probe failures. If pods are healthy, I verify the service selector matches pod labels and that endpoints exist. Next I check ingress rules, target ports, security policies, and load balancer events. This sequence narrows the issue from chart rendering, to workload health, to service discovery, and finally external networking. In your answer, describe checking release status, rendered manifests, pod events, logs, probes, services, selectors, endpoints, ingress, security policies, and cloud load balancer events. Distinguish template errors from runtime and networking failures. Question 8. Explain Kubernetes readiness, liveness, and startup probes, and how poor configuration causes outages. Readiness answers whether a pod should receive traffic. Liveness answers whether Kubernetes should restart it. Startup protects slow-starting applications from premature liveness failures. I configure readiness around dependencies required to serve safely, but avoid making every transient dependency failure trigger restarts. Liveness should detect a stuck process, not ordinary latency. I tune periods, timeouts, thresholds, and startup windows using measured behavior. Poor probes can remove healthy capacity or create restart storms during an otherwise manageable dependency outage. Mention each probe's purpose, HTTP or TCP or exec mechanisms, startup protection, failure thresholds, initial delays, timeouts, and rollout behavior. Emphasize that liveness should detect unrecoverable states, while readiness controls traffic rather than restarts. Question 9. How do Kubernetes requests, limits, COS classes, and eviction interact? Requests tell the scheduler how much capacity a pod needs, while limits cap runtime usage. CPU limits can cause throttling, whereas exceeding a memory limit commonly causes an OOM kill. Kubernetes derives COS classes. Guaranteed when requests equal limits for every container, burstable when requests exist but differ, and best effort when neither is set. Under memory pressure, lower priority COS workloads are more vulnerable to eviction. I set requests from observed usage, review them continuously, and avoid arbitrary limits. Be sure to explain CPU and memory requests, scheduling, limits, throttling, kills, guaranteed, burstable, and best effort COs. Include realistic sizing, limit ranges, monitoring, and why incorrect limits can destabilize workloads. Question 10. How would you implement safe application deployments and rollbacks in Kubernetes? I make deployments reversible and observable. A rolling deployment uses readiness probes plus carefully chosen max unavailable and max surge values, so capacity remains available. For higher risk changes, I use canary traffic, compare error rate and latency, then promote automatically only when metrics stay healthy. Database changes must be backward compatible across versions. Helm or GitOps records the desired revision, while rollout history supports rollback. I also define explicit abort criteria because a fast rollback is safer than debating during an incident. Discuss rolling updates, max unavailable, max surge, readiness gates, revision history, canary or blue-green strategies, backward compatible schemas, Helm rollback, observability, and automated promotion. Connect deployment safety to financial service availability and auditability. Question 11. How do you manage secrets in Kubernetes and AWS EKS? Kubernetes secrets are useful objects, but base 64 encoding is not protection. I enable encryption at rest, restrict RBAC, and prefer an external manager such as AWS Secrets Manager or a compatible enterprise vault. Workloads access secrets through tightly scoped service identities, ideally using a CSI driver or external secrets integration. Rotation should be automated and tested, with applications able to reload values safely. I prevent leakage in Git, Helm output, C logs, crash dumps, and diagnostic commands, then audit every access. Cover the risks of Kubernetes secret objects, encryption at rest, external secret managers, IAM roles for service accounts, rotation, access auditing, templating boundaries, and preventing secret leakage through logs, manifests, and C systems. Question 12. How would you diagnose intermittent networking failures between pods in EKS? I troubleshoot from the application outward. I verify DNS resolution, pod IP reachability, service endpoints, and ports using a temporary diagnostic pod. Then I inspect network policies, security groups, route tables, VPC CNI logs, available subnet IPs, and node conditions. For intermittent failures, I compare affected nodes, availability zones, timestamps, and flow logs, while checking MTU and connection exhaustion. I avoid restarting components before collecting evidence. Reproducing the failure with a minimal client often separates application issues from platform networking. Focus on DNS, SINA and IP allocation, network policies, security groups, routes, services, kube proxy or dataplane behavior, MTU, node health, and flow logs. Explain a layered troubleshooting process using evidence rather than random restarts. Question 13. What is the Kubernetes scheduler considering when placing a pod, and how would you influence placement? The scheduler first filters nodes that cannot satisfy resource, taint, affinity, or policy requirements, then scores feasible nodes. I influence placement with node labels, node affinity, taints and tolerations, topology spread constraints, and pod anti-affinity. For critical replicas, spreading across zones and nodes reduces correlated failure. Dedicated node groups can isolate sensitive or specialized workloads, but over-constraining placement causes pending pods and wasted capacity. I validate decisions through scheduler events and resource metrics rather than relying solely on manifest intent. Mention resource requests, node selectors, affinity and anti-affinity, taints and tolerations, topology spread constraints, priorities, capacity, and zone awareness. Explain balancing isolation, utilization, availability, and operational complexity. Question 14. How would you build observability for a Kubernetes platform supporting critical services? I combine metrics, structured logs, traces, and Kubernetes events. Platform dashboards cover API latency, scheduler behavior, node pressure, resource saturation, CNI health, pod restarts, and deployment status. Service dashboards focus on latency, traffic, errors, and saturation, tied to SLOs rather than arbitrary thresholds. Correlation IDs connect a customer request across services. Alerts should be actionable and routed by ownership, with runbooks and retention policies. For regulated systems, I protect observability data and preserve required audit evidence. Discuss metrics, logs, traces, Kubernetes events, golden signals, control plane and node health, application SLOs, correlation identifiers, alert quality, retention, access control, and incident workflows. Include actionable dashboards rather than collecting data without purpose. Question 15. What is the role of the Kubernetes Horizontal Pod Autoscaler, and what can make it ineffective? HPA adjusts replica counts from observed metrics, commonly CPU or memory utilization relative to resource requests. It works well for stateless workloads when metrics reflect demand, but CPU may be a poor signal for queue-driven or I/O-heavy services. I may scale on queue depth, request rate, or latency through custom metrics. I configure stabilization and scale up or scale down policies to avoid flapping. HPA creates pods. Cluster autoscaler or carpenter must provide nodes, so both layers require capacity planning. Explain metric collection, utilization targets, scaling behavior, requests, stabilization windows, custom metrics, cluster autoscaler interaction, cooldowns, and workload suitability. Mention queue depth and latency as alternatives to CPU for many services. Question 16. How would you design a platform engineering model that enables developer self-service without sacrificing governance? I would provide a paved path. A service template that creates a repository, C pipeline, Helm configuration, observability, security checks, and deployment policy automatically. Developers self-serve through a portal or pull request, while platform guardrails enforce identity, image provenance, resource standards, and approved environments. GitOps gives auditable changes and consistent reconciliation. Teams retain ownership of application behavior, with documented escape hatches for legitimate exceptions. I measure platform success through lead time, reliability, adoption, and reduced operational toil. In your answer, cover golden paths, reusable templates, GitOps, policy as code, RBAC, service catalogs, paved road defaults, escape hatches, documentation, ownership, cost visibility, and feedback loops. Emphasize platform products rather than ticket-driven infrastructure. Question 17. How do you approach Kubernetes cluster upgrades, especially for EKS? I begin with an inventory of deprecated APIs, admission webhooks, add-ons, controllers, and workload disruption budgets. I test the target version in a representative environment, back up critical state, and confirm capacity for draining nodes. For EKS, I coordinate control plane, managed add-on, node group, and client upgrades according to compatibility guidance. I upgrade a canary node group first, observe workloads, then roll forward gradually. Because control plane rollback is limited, preparation, maintenance communication, and rapid recovery procedures matter. Cover version compatibility, deprecated APIs, backups, upgrade sequencing, control plane and node groups, add-ons, admission webhooks, pod disruption budgets, capacity, canaries, rollback limitations, and post-upgrade validation. Question 18. How would you investigate a Kubernetes incident where pods are repeatedly restarting after release? I correlate restart timing with the release, then inspect rollout history, pod events, current and previous container logs, exit codes, and termination reasons. I compare rendered manifests, images, configuration, secrets, probes, resource settings, and dependency endpoints against the last healthy revision. Killed suggests capacity or leak investigation. Probe failures may indicate startup or dependency behavior. If customer impact is growing, I pause or roll back using a known good revision, while preserving evidence. After recovery, I fix the detection gap and document contributing factors. Mention rollout correlation, container exit codes, previous logs, events, probes, configuration and secret changes, resource pressure, dependency failures, image differences, rollback criteria, and preserving evidence for post-incident analysis. Question 19. How would you use Kubernetes network policies to isolate workloads while preserving required communication? I start with a default deny policy, then explicitly allow required ingress and egress by namespace, pod labels, ports, and trusted external destinations. DNS access must be permitted, and policies should reflect application communication rather than broad subnet ranges. Since policies are additive, I review all applicable rules together and verify that the chosen EKS networking implementation enforces them. I test in staging with representative traffic, monitor denied connections, and document ownership. Least privilege is valuable only when operationally validated. Explain default deny ingress and egress, namespace and pod selectors, ports, DNS exceptions, policy union behavior, testing, observability, and avoiding accidental outages. Mention that provider support and enforcement must be verified in EKS. Question 20. Describe how you would manage Kubernetes infrastructure and Helm releases through C, CD or GitOps. I keep infrastructure, application manifests, and Helm charts versioned, reviewed, and promoted through controlled pull requests. C builds and scans images, lints and renders charts, validates policies, and runs deployment tests. GitOps then reconciles approved state into each environment, detecting drift and providing an audit trail. Secrets are referenced externally, not committed. I separate cluster changes from application releases where practical, use progressive promotion, and retain rollback versions. This approach improves consistency while still allowing emergency changes through documented, audited procedures. Be sure to cover source control, pull request review, image scanning, chart testing, rendering, policy checks, environment promotion, drift detection, approvals, secrets, rollback, auditability, and separation between infrastructure and application changes. If you are still with us, congratulations! You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.